Inductors. Again, just like capacitor, the symbol for inductor, it's a coil. It's a wire wrap that looks like this. Has the value L in Henry. The units for that's Henry. It has a voltage here, plus to minus, we call it V. There's a current going through, that's I. In capacitor, we said I equals what? C dV dt. This is backward. Here, the voltage across the inductor, it's L di dt. Yep. So now, if you look at that just like this, I'm trying to compare it to this one. Let's look at this one. We discussed in terms of DC source, which means constant, but not constant voltage here, constant current. If you have a constant current, what's the derivative of any constant? Di dt will be 0, which means your voltage will be 0. For an inductor to have a 0 voltage, that means it's behaving as what? Can't be open. Behaves as short circuit, wire. It behaves as a short circuit. The capacitor behaves as an open circuit. And just like we said, since the voltage cannot change in 0 time because you'll have infinite current here, guess what? The current through the inductor cannot change in 0 time. The current I sub L at t equals 0 minus, and the current at t0 plus is going to be the same. It doesn't change. The current does not change in 0 time. We can derive the equation for the current just like we did with the capacitor. Looking at that equation, leave a space. Let's multiply both sides of the equation by dt. This cancels that. Divide by L, 1 over L, the integral of the voltage, dt, equals the integral of I. I'm sorry, di. Right? di. What's the integral of di? So the current through the inductor at any given time is 1 over L, the integral from negative infinity to t v dt. And if you want to break it down, just same thing we did with the capacitor. We said I can break it down to two integrals. One from negative infinity to t0, 1 over L in the front, plus 1 over L, the integral from t0 to t v dt. For those people who forgot, there's a rule in calculus that says the integral from a to b plus from b to c, that's the same as the integral from a to c f of x dx, right? So that's what I did here. I used that rule. Well, the answer to the first one is the current at t0. So the answer to this is I sub L at t0. Add to it 1 over L, the integral from t0 to t v dt. Clean it a little bit there. I sub L of t equals what? 1 over L T0 to T V dt plus the current at T0. We'll derive the equation for the energy there too in a second. Let's try an example. Leave a space on the left a little bit there. Notice I'm moving my axes in the middle here. Let's say that this is the current, I. This is the time, t. And my current looks like this. This is -1. This value is 1 here. Then stays 1 for a while.
Are you just making this up?
Yep. Making something up. Then it comes down like this. And this value is 2 seconds here, and that's 3 seconds. And I want to find what the voltage is. So I'm making this one up. Assume this is your current through the inductor. We have an inductor, and the inductor has a value of 3 Henry. So I'm giving you the current going through it. That's I. Can you tell me what the voltage across the inductor will look like? Well, if we look at that one, if you look at it, that looks like a straight line. So if I can find the equation of it. So here we go. It's a straight line. Is the slope positive or negative? Positive. So that would be mx plus b. The slope is the rise over the run. What's the rise? 1. What's the run? 1. That's 1 over 1, which is 1 t. And what's the y-intercept? 0. For t greater than or equal to what? -1 and less than 0. Before that is 0. You can see there's nothing before that. Between the 0 and 2 second, this is a straight value. That's just constant, 1. For t greater than or equal to 2, but less than or equal to 3. Doesn't matter if I put equal sign or not, because right there the same value right here. So now that's decreasing. What's the slope? -1. That's a minus t, but it has a y-intercept. Notice, if you continue with that graph, every time you go to the right one, you drop 1 unit. So if you go backward, that'll be a 2. 1 more will be where? A 3. So this has a y-intercept actually of 3 if you extend the line. mx plus b.
Isn't the first one t plus 1?
What's the y-intercept? 1, yes. Thank you. Yep. mx plus b. b is the y-intercept. So this has a y-intercept will be a 3. Now I want to find what the voltage, V equals L di dt. So to the left of this, remember for t less than -1, what was the value? 0. For t greater than 3, what was the value? 0. So let's find V equals L di dt. And L equals 3 Henry. So what's the voltage? For the first one, for t less than -1, what's the derivative of 0? 0 times 3 is 0. For t between 0 and -1, what's the derivative of this one? This function, t plus 1. 1. 1 times the 3? 3. For t between 0 and 2, what's the derivative of 1? 0 times 3? 0. For t between 3 and 2, what's the derivative of this? -1. -1 times 3? -3. For t greater than 3, what's the derivative of 0? 0 times 3, which is 0. Can I graph that now? It should look like a square wave. This is the -1 right here. It should look like this. It has a value of 3. And it comes down and stays 0. Then it goes down to what? -3. Then it goes back to 0. This is the -3. That's what the voltage across that inductor will look like if you supply that current. There'll be a 0 voltage here. There'll be a 3 volts here, -3 volts, back to 0, back to 0. Yes?
Is it actually that, like, instant, though?
Well, it won't be that instant. We'll just, actually, the newer one's really quick and sharp, so we'll look like this. You know? It's hard to see them, but you'll see like a little drop there. You know? When we used to use our old scope, you'll see a little spike in the scope at that time. Go and it goes like this, you know. But it's not much like it doesn't take like half an hour to go up there. It really milliseconds, microseconds to go. So you have to change the scale on the x-axis to see them even more, you know. We're working on make it ideal, but it's not happening yet. Now, what about the energy? Just like we did with that capacitor. I'm rushing. I feel like I'm rushing through, trying to finish in time. I spend more time on the capacitor, but you get the idea, I think, for both, because they're identical almost. We said the power, it's V times current. V is what? L di dt times I. So the power is L I di dt. Energy is the integral of the power. The energy stored in an inductor, you can factor the L out, the integral of I di, because the dt here cancels that dt there. So what do you end up with? 1/2 L I squared. One-half Li squared. An example quickly. We'll do more examples next class, but let's say we have 12 sine. That's a source of pi t over 6. So we have a current source, AC current source, pushing current through a resistor of 0.1 ohm and an inductor of 3 Henry. We used the 3 Henry last time. Let's stick with it. And the question, can we figure out what the voltage here is, VR, and what's VL? If we know what that is, we can figure out what the voltage across the source here if I need it. Then we'll calculate how much energy stored in that inductor. Well, the energy stored, I can do it already quickly. 1/2 Li squared, right? So the energy, I can do that. It's 1/2. We know L is what? 3. What about the current through the inductor? That's the same current, right? 12 sine pi t over 6. And don't forget to square that. 1/2 Li squared. Square the 12 is 144. Divided by 2 times 3. 144 divided by 2 times 3. 216, you mean. 216, bless you, sine squared pi t over 6. That's the energy. Can I figure what VR is? The voltage across the resistor? Ohm's law. V equals I times R. So 0.1 times 12, that would be what? 1.2 sine pi t over 6. What is the voltage across the inductor? VL. V equals L di dt. L is 3. Let's take the derivative I. Here's a 12. The derivative sine pi over 6t is what? Pi over 6 times cosine pi t over 6. That would be 2 times 3 is that 6 here? 6 pi cosine pi t over 6. You want to find the voltage across the source, you add both of these. Why? Sum of the voltage in the closed loop is 0. Okay, VL. So we know everything about them. Next time, actually, we're going to work with capacitors and inductors. What happens if you have more than one capacitor, more than one inductor? But before I leave the topic, let me put them side by side and just show you what we talked about. I'm going to split this one into, the paper into two things. Capacitor on this end, inductor on that end. The symbol for a capacitor is this way, and this voltage is V. The capacitor has a value of C in Henry, and this is the current I going through it. Inductor, it's a coil. This is the voltage V. The value is L in Henry. This is in farad, and the current going through it I. Here we said I equals what? C dVc dt. You take The change in the voltage, take the derivative of that, times C. This one says V equals what? L di dt. Very similar. We switch I and V basically. V here, it's 1 over C, the integral from negative infinity to t of I dt. This one, I as a function of time equals 1 over L, the integral from negative infinity to t of V dt. You can break both of these into two parts. You can go 1 over C from t0 to ti dt plus the voltage across the capacitor at t0. And this one you can say 1 over L, the integral from t0 to t V dt. I don't know why I have this one close here. V dt plus the current through that inductor at t0. The energy, 1/2 C V squared T, the energy stored. The energy stored, 1/2 L I squared. To DC, the capacitor behaves as what? Open circuit. To DC, the inductor behaves as what? Short circuit. And the last thing I'm going to write, that the voltage across the capacitor is 0 minus, or T0 minus, is the same as the voltage across the capacitor is 0 plus. It doesn't change in 0 time. The inductor, the current through the inductor is 0 minus, is the same as the current through the inductor is 0 plus. So the current does not change in 0 time. Those become really important when we get to the next chapter. These two, the last two. When we start dealing with RC, RL, RLC circuits. So they're side by side, the two of them. That was a clicker there. So I'll stop here since we're out of time. And for homework assignment, we are in the next chapter now. That's chapter 7. I can tell you we're going to do so all the stuff we did, energy and everything. 7.1 to 7.7. 7.1 to 7.7.
What page is that?
They start in chapter 7, which is page 220.
Still recording.
Huh?
Still recording.
Still recording? Oh.